So, welcome everyone. Today we will take a small excursion into the world of asymmetric trust, and in particular we will explore the question of which properties should asymmetric quorum systems satisfy. So, when we work with distributed systems, we have to make assumptions because failures are inevitable. So there can be things like network errors, software bugs, machine crashes, or just malicious participants. So if we want to be able to solve problems, we need to make assumptions. Perhaps the most common assumption out there, and perhaps the one you are most familiar with, are what we call threshold assumptions. So we have a set of n processes. Some are correct, some are faulty, and the assumption that we make is that at most f of these processes will be faulty. And this f changes depending on the setting, but the assumption at the heart is that we will have a bound on the number of faulty processes. We can go a bit in this thing and define what we call symmetric generalized assumptions. So in the threshold case, we just say any set of f participants will be faulty in the worst case. But now, instead of defining just these sets by size, we can just define these sets however we want. So what we do is we define what we call quorums, which are sets of processes that should not fail together. For example, here we can define one quorum, and find another quorum, and another quorum, and then some are correct, some are faulty, and the assumption that we make is that at least one quorum will have no faulty processes. So here, this quorum, all the processes are correct, so in this case, the assumptions hold. An important thing to note about these quorums is that they have to be shared by all the participants in the system. But actually, when we go outside in the real world, trust is a bit more subjective. I do not trust the same people that you trust. So with threshold and symmetric assumptions, we get this undesired behavior that everyone has to share the same assumptions. But actually, what we propose is that each process should be able to determine who it trusts independently. So what we do is, instead of having symmetric generalized assumptions, we have what we call asymmetric generalized assumptions. So now, each process is free to define its own quorums. For example, process 1 comes and says, I like these quorums, and decides on this. Then, another process comes and says, I do not like those quorums. I want to define these quorums instead. And it's free to do as it wants. So now, each process has its own quorums. Also, we have some processes that are correct, some processes that are faulty. And then, the assumption that we have to make is that if I defined my quorums correctly, then at least one of my quorums will have no faulty processes. If you think about this a bit more, it's just a symmetric assumption, but generalized to each process independently. So for example, here, quorum 1 has the quorum number. Process 1 has quorum 1, which all has correct, so in this case, the assumptions it made work. But process 2 comes, and its quorums were not so well defined. There is a malicious party in each quorum, so in this case, its assumptions will not work.
Yeah. I mean, sometimes the definition of malicious is not so symmetric either, in the sense that process 2 may trust him because he trusts that he will not damage process 2. He doesn't care if he damages process 1. So, have you generalized that far?
No, we haven't. So, yeah. So this is what we call asymmetric generalized assumptions. So the theory behind this was defined already quite some years ago in this paper by Damgaard and others. And a couple of years ago, this theory was further developed in this paper by Alpos, which is in the room with us today, and others. And in here, they took the original theory about asymmetric generalized trust, and they developed algorithms for problems like reliable broadcasts and consensus. So this is not the only asymmetric trust model there is out there. So for example, these are some other papers which describe similar but slightly different asymmetric trust models. And yes, for the rest of this talk, we will focus specifically on this asymmetric trust model. So asymmetric trust is not just a theoretical thing. There are projects out there using these concepts. So for example, the two most, perhaps the two biggest ones are the XRP Ledger and Stellar. So let's take a step back and just define our model in which we will work. So we have a set of processes, and each process defines its own quorums, and we assume that all processes know the quorums that each process defines. Then we also assume asynchronous communication, and in terms of faults, we will consider Byzantine faults.
So 1 second. If you consider Byzantine faults,
yeah.
and I tell you that my quorums are, a particular set, and I tell someone else a different story.
Yeah.
How does that fit in here? That's still, or is all correct? Are the quorums of all correct members known to everybody? I mean, your second line here assumes everybody knows, but if I'm Byzantine, I could communicate these in an inconsistent way.
Yes. So what we will actually see is that it doesn't really matter what you say, as long as the correct processes define the same quorums for...
So for correct processes, this is true.
Yes. Okay. So when we come into the asymmetric trust, the first thing that we see is that processes are not correct and faulty anymore. So in the threshold and in the symmetric case, we can just say, I am a process and I am correct, or I am a process and I am faulty. This is not the case anymore. Because imagine we have a correct process, but it's defined its quorums incorrectly. That is, its trust assumptions were not right about who it should trust. So based on this, we have now 3 classifications for processes. So we have the faulty processes, which stays the same. But now the correct processes, we have 2 subclassifications. We have what we call naive processes, which is a correct process, but where all its quorums contain at least one faulty party. And then we have the wise processes, which is a correct process and also where it has at least one quorum with no faulty parties. So now let's take a look at how do the problems differ between symmetric and asymmetric trust. So in the symmetric case, for example, for reliable broadcast, in the consistency property, we just say if a correct process delivers a message and another correct process delivers a message, then these 2 messages have to be the same. But now, in the asymmetric trust, we don't have just correct processes anymore, so we have to be a bit more, to go a bit more in detail on what we say. So, for example, the consistency property, we redefine it as saying that if a wise process delivers a message and another wise process delivers a message, then these have to be the same. So you can see that in general, we just go a bit deeper into the characterizations of processes. So now that we have seen the asymmetric trust world, let's come to the important part of this talk, which is the properties that asymmetric quorum systems should satisfy. So in the symmetric case, normally we just say that consistency and availability properties are enough to solve problems like reliable broadcast and consensus. So in the consistency property, we just assume that any 2 quorums will intersect in a correct process. And in the availability property, what we ask is that at least one quorum has no faulty processes. And if these 2 properties hold, and then we can use this symmetric quorum system and solve, let's say, consensus or reliable broadcast. But now we come to the asymmetric quorum world. So consistency and availability, we still want this to hold. But actually we need a little bit more, because it was proven that if your asymmetric quorum system only satisfies these 2 properties, it will not be possible to solve reliable broadcast and consensus. So we need or perhaps we can just call them stronger assumptions. So the solution to this problem by the paper I mentioned before is what they call a guild. So a guild is just a set of correct processes that contains a quorum for each member. So basically we have the whole set of processes, we identify some processes, and if all processes have one quorum within this set, then we can say that this set of processes is a guild. And as you can see, for example, one very direct conclusion of this is that there can be guilds within the guilds. So there we can have one guild, and then we can have another guild that is a superset of the original guild. But just the main point of this is that if we have this characterization, then we can solve reliable broadcast and consensus. So this paper, based on the assumption that the execution has this property, was able to provide solutions for these two problems.
But for guild, like, also the quorums have to be fully contained in the guild.
Yes. Each one, so if I am a member of the guild, I need to have at least one of my quorums be in this guild. So yes, as I was saying, if we have a guild, then we can solve reliable broadcast and consensus. So how do we take into account guilds in the reliable broadcast problem? So for example, we redefine the validity property to say that if a correct process broadcasts a message, then all processes in the guild will be able to deliver the message. And the same for the totality property. We just assume that all processes in the guild should deliver the message. And guilds have similarities in other asymmetric trust models, although they are not exactly the same. The models, for example, the first one uses what they call consensus clusters, and the second one uses what they call strong availability. But at its heart, they are quite similar. They are basically just a set of correct processes where you can find a quorum for yourself. But when you see guilds, and this kind of brings you memories of symmetric trust, then I would say you are right. Guilds smell kind of symmetric at its core. So what we found is that if you have an execution where there is at least one guild, then you can take the asymmetric quorum system and from it apply some transformation and build a completely valid and equivalent symmetric quorum system. And if a process adopts this new symmetric quorum system, then it will not be worse off in the resulting execution. So basically, if we have a guild, you can just apply this process, build the symmetric quorum system, and just use normal symmetric trust algorithms. So you no longer have to go to the hassle of having to design asymmetric algorithms. So how do we do this? The idea is to treat each possible guild as a quorum. So what is a possible guild? So a possible guild is just a set of processes that would be a guild in some execution. So you consider all possible executions, and if this set of processes would be a guild there, then you can treat this as a quorum. So yes, the new symmetric quorum system is just the set of all possible guilds. But we have a small problem, is that there is potentially an exponential number of possible guilds. So
when you mean in any execution, is there an assumption about false or really any?
So you take any execution, so you assign correct, faulty to processes however you want. And if there is some guilt in this execution, then you treat this as one possible quorum. So just consider all possible assignments, and just, if there is a guilt, it's a quorum. So this has a small problem, which is that there is a potentially exponential number of possible guilds. So the new asymmetric quorum system is huge. So if you want to build it, it becomes a bit of a problem. Actually, you don't need to build the new quorum system. Normally, when you have an algorithm, what you need is to recognize if what you have is a quorum. So yes, we transform the problem from building the new symmetric quorum system to just recognizing its quorums. And how do we do this? Well, it turns out you can recognize guilds quite efficiently. So basically, if you have a set of processes, just for each process, you check if it has a quorum within this set of processes, and if yes, then this is a guild in the execution where all the members of this set are not faulty. And for this, we have to assume that you can recognize quorums efficiently, but I think this is quite common. So a similar result was found. Yeah.
Are we, like for the guild detection,
Yeah.
checking like for a given set of processes, but don't you need to know the other like processes and quorums for this?
Which we assumed on a slide back, right?
Did we?
Yes.
Okay, I missed it.
So a similar result was found in the crash fault model in the synchronous Byzantine. Sorry, in the synchronous crash fault model, you can take an asymmetric quorum system and build an equivalent symmetric symmetric quorum system. But this you no longer require a guild, so basically this just works all the time. So from this paper, you can just conclude that it makes no sense to use asymmetric trust in the crash fault scenario. So the current situation is as follows. We know that to solve reliable broadcast and consensus, this will only work if you have a guild. But guilds imply symmetric trust. So basically it makes, as we are right now, it makes no sense to use asymmetric trust in the Byzantine fault scenario. So what we need to do to solve this problem is to find solutions to asymmetric reliable broadcast and consensus where we do not need guilds anymore. So how do we proceed? So guilds are way too strong, but consistency and availability are too weak. So we need to find something in the middle that is neither too strong nor too weak. So we explored this in this paper, and what we found is the following. So imagine you have this very simple algorithm. You just, in the start, you send a message. Upon a quorum of these start messages, you send an echo message. And then upon a quorum of echo messages, you finish the execution. So imagine what do you require if you want to send a finish message. So from following this algorithm, we can see that you actually require a quorum of echo messages. And for a process to send an echo message, what does it require? It requires a quorum of start messages. And in the end, basically what you require is that some set of processes send start messages. And in this specific case, this is just that the quorums of a quorum should send a start message. And if you kind of look at this like a tree, you can see that this is just like a two-level tree of quorums. So, inspired by this idea, we defined the notion of the depth of a process. So a correct process has depth 0 just by definition. And then furthermore, we say that a process has depth d if it contains a quorum such that all its members have depth at least d minus 1. So if I am a process and I have one quorum and all its members have depth d minus 1, then I will have depth d. And from this definition, you can see that a process can have multiple depths, but we actually just care about the maximal depth of a process. So here, in the example, you can just think of this process to finish. It just requires having depth 2, so 2 sequences of quorums. So let's take a look at some examples of how do we define depth. So if we have this process here with these 3 quorums, we have that it has at least one faulty process in each quorum, which causes this to have depth 0. And this is what we just, before what we called naive processes. Then let's consider this other process. Here in the circles inside what I put is the depth. And in this case, what is the depth of this process? Well, it has one quorum where all are correct, and all have depth at least 0. So basically, this process here has depth 1. And similar for this case, we take a look at the quorums and find the minimum depth that all the processes in the quorum have. And for example, in this case, this is 1, so this process has, this process has depth 2. it's incorrect in the slide. So yes, so we have defined this new notion of depth. And actually this generalizes the existing classification we had before. So before, what we called naive, now it's just a process that has depth 0. Then what we call a guild member is basically just a process that has depth infinity. Basically that it can always go on and on within its quorums and find the correct processes. And before, what we called wise processes are just all the depths from 1 to infinity. So you can see that with this new characterization, we get much more expressivity. So now that we have defined the notion of depth, we actually need to solve problems with this. So we first have to adapt asymmetric problems to use depth. And what we want to find is if we can find a solution to some problem such that we can solve it for some problem for all processes with some bounded depth. So basically before, guild equals depth infinity. So if we can solve this problem for processes with some depth, let's say d, then we don't need guilds anymore. So this is the objective we want to. Yes.
So it seems that depth has to do with liveness, right? But are you going to make liveness?
Yes.
Are you going to make an assumption that all the quorums intersect anyway, or something like that?
We assume that all quorums are intersecting, yes. So that's the standard consistency and availability properties we require, but depth comes a bit, and that's a bit more of requirements here. So yes, what we are looking for is for algorithms that solve problems for processes with depth less than infinity. So we start with the reliable broadcast problem. So the first thing we do is to adapt the properties of the problem to use depth. So for example, we redefine the consistency property to say that if a process with depth d delivers some message and another process with the same depth delivers another message, then these two messages have to be the same. And we do similar things for the other properties of reliable broadcast.
Is this for a fixed d?
Yes, so basically what we want to do is find a minimum d that solves this, that has these properties. So before, in the ACT set paper, they give an algorithm for reliable broadcast with depth infinity. And we proved that you cannot solve this for depth 0 or 1. And yeah, the next step we want to do is find the minimum depth for which we can solve this. And let's take a look at the algorithm they proposed. This is the algorithm with guilds or also depth infinity. So this is basically just Braha broadcast with asymmetric quorums. And here they use what they call the notion of a kernel, which is just a set of processes that intersects all of my quorums. So the algorithm is as follows. You deliver a message upon receiving a quorum of ready messages. And then you also have this other instruction that says that if you have a kernel of ready messages, then you kind of amplify the ready message. And this instruction here just guarantees that if one guild member delivers, then all guild members will deliver. And since we have guilds, this is the key insight, is that the kernel will contain at least one guild member. So if you basically amplify a ready message, it will be with the correct message value. And why does this not work with depth less than infinity? Well, it turns out that malicious processes can trick a process with depth 0 to amplify incorrect messages. And by this, you can continue and trick a process with depth 1 to send incorrect messages. And you can just go on, and this basically allows you to trick any process with a finite depth to send the incorrect message. So this is the problem with the current algorithm. And what we did is modify it a bit. So basically what we did is just add one extra quorum requirement in the amplification step. So now we still have that malicious processes can trick a process with depth 0, but now because of the quorum requirement, to trick a process with depth 1, you need a quorum, and because of the quorum intersection property, this cannot be composed only of processes with depth 0. So basically now, malicious processes can only trick processes with depth 0, but not 1 or above. So what we did is we proposed this algorithm, and it turns out that it solves this problem for depth 3. So basically we reduced the assumption strength from infinity to 3, but it's still an open question if you can solve this for processes with depth 2. And the next question that you might ask yourself is what happens with consensus? Basically, does consensus have bounded depth? And unfortunately, I cannot give you an answer today. The main challenge for this is that consensus can have executions with infinite length. So this kind of puts you in a position where you have to require a quorum of yours to be alive, and so on and so on. So it kind of looks like it should have infinite depth, but I cannot say with certainty if it's true or not. But this is a good question, because does consensus have infinite depth? Well, it turns out that either way, the answer is interesting. So if consensus has infinite depth, then we just reached the conclusion that it doesn't really make sense to solve consensus in the asymmetric trust model, because you can use the equivalent symmetric algorithms instead. And if the length of consensus is bounded, then we also get an interesting result, because the algorithm will be interesting by itself. But also it tells you that it does make sense to use asymmetric trust for consensus. So as an overview, today we saw first that existing field assumptions are too strong, so strong in fact that using asymmetric trust becomes unnecessary, and we proposed using depth to replace these assumptions. And with this we were able to weaken the assumption of reliable broadcast from infinity to 3. And if you are interested by this and want to solve some problems, then there are quite some interesting ones available. So for example, the first one is finding an answer to the depth of consensus, and then also just finding the minimum depth to solve reliable broadcast, and eventually, if consensus has finite depth, also for consensus. And finally, you can ask yourselves if other asymmetric trust models have a similar guilt effect that basically invalidates the benefits of asymmetric trust. Thank you.
Thank you very much. Any questions? Yes.
So for consensus, you would get infinite executions if you want success with like probability 1, let's say. But like if you're doing, let's say, like a cryptographic algorithm and you accept a small probability of failure, then like you don't get maybe infinite executions anymore. Would there be, could it be possible to bound the depth when that is the case, maybe?
I think in this case it should be possible, yes.
I also had one more question for the quorums. I think you said like every 2 quorums should like intersect with the, but that seems to be like, for the threshold case, that seems to indicate like the majority honest or like f less than n over 2. But shouldn't it be like n over 3 in like an asynchronous setting? Did I miss?
In the Byzantine setting, it's
Yes.
f over 3.
So that's like every 3 quorums have like an intersection.
And maybe circling back quickly to the questions asked during the talk. So now that you've talked about everything, so maybe I still missed it a bit. So you said that it really doesn't matter that we assume at the beginning that everybody knows everybody else's quorum. Can you now detail it maybe again quickly? Because the model is everybody knows everybody's quorums, right?
Yes.
And you say it doesn't really matter, like you will get the same results if you did not assume that, or what?
Yes, because what I mentioned, we require global knowledge of the quorums of everybody else.
Yes.
But if you are a malicious process and you define your quorums however you want, it doesn't really affect us because the requirement that we put is on the quorums of correct processes.
So basically, in some sense, here what you do is somebody gives you a template, as in these are the quorums of everybody. You design a protocol or you analyze whether protocols exist for that collection of quorums. Right? The same way you can assume you know n, and usually you do. You can assume you know the quorums, and that's the setup. Okay.
But so following up on that, so you have this algorithm that computes new quorums out of guilds, right? To transform from asymmetric to symmetric. But that algorithm needs as input the quorums of everybody, right?
It requires this, yes.
So are you saying that if two different correct processes have different quorums for the Byzantine processes, it will not matter? The output of the algorithm will be equivalent in some way, or?
Yes, because these are on the malicious processes. So in any case, they would be not good quorums in the end.
Mm-hmm.
It will not affect the guilds because they're Byzantine, right? That's the key.
So, yeah. So you presumably don't know who the bad processes are. So if you see two processes with different quorums, you somehow know that one of them isn't good. Or something. Yeah, so, yes.
It's also like when you do this transformation, I guess you can imagine it as a transformation of problems, right? Like one of them is a problem where you have this set of asymmetric quorums and you can map it to another problem where you have symmetric quorums, and there is also a mapping of how protocols here correspond to protocols there, like, but you can also see it like very from, high level.
So if you assume you've got a majority of good processes, then a majority of the processes are going to have the same quorums, and so it's trivial to work out what the quorums you want are. It's also trivial to see all the people who are different that must be bad, although clearly some bad people may also have the same quorums. So there can be no motivation for a bad person to have different quorums under that model.
But here you're also allowing good people to have different quorums
Oh,
just because
right.
they have different ideas.
Oh yeah, well I was trying to get at the truth of this, yeah. Yeah.
So,
And we'll study it more carefully offline, I think. Study it.
any other questions?
Like maybe also following up on that in a more practical sense. So you mentioned how, like, for instance, Stellar does something like this, and I don't know about the other one, but like, is there an immediate, short answer for how it's actually done in practice? Because kind of we are like circling also around what does it, how do you get to the point where you know the quorums, right? So like, how is it actually done in practice? Like, if you know what I mean, like, because here we start from the assumption you know all the quorums. Okay, how do you get there? Kinda.
So, if I am correct, and you can correct me if I am wrong, I think in Stellar, when you query a process, you can query it to ask for its quorums, and it will tell you your quorums back.
A big difference in Stellar is that we don't assume they intersect. And it turns out it still works.
Right.
So we have this notion of intact set, which is a bit like a guild, I guess, or well, not sure. But and then we prove that even if things don't intersect, the intersection of two intact set is also an intact set. And so your system is basically an island of consistent sets of processes. Set of islands, there's a partition.
That's very cool.
Yeah, I mean, following up on that, have you thought about removing this assumption that there is intersection between all the quorums? And that might be another interesting direction, right?
I am currently thinking about doing this with a model similar to this. So trying to find out if it's possible to obtain a similar reduction in this case.
Okay. We have a few more minutes if there's any other question, but otherwise let's thank the speaker again.